So today we will talk about a pre-Rust. So basically, because Rust is a low-level language, my original plan was I want to talk about Rust, but I put like every prerequisite knowledge, low-level prerequisite knowledge, and it's already one contents on its own. So that's why now we don't talk anything about Rust, but more about like CPU and then memory and then like how it fits in Linux process. So okay, so CPU. So talking about CPU, so we will talk about this guy here. So he's Hungarian. So maybe I want you to kind of guess like who is this guy, or maybe some of you already know who is this guy, if you know. So basically, he's like one of the most intellectual of the 20th century. So he contributed to physics, to mathematics, game theory, and of course, computer science, right? In terms of CPU architecture. So he's Hungarian. So he has a Hungarian name, János Lajos. So if you know anything about Hungarian, so Hungarian language is not considered as a European language because it sounds so different. Um, so he's also took part in Manhattan Project in Los Alamos. So if you uh, watch Oppenheimer, so basically he also lived in Institute for Advanced Studies in Princeton, like Oppenheimer. So if you watch Oppenheimer in the in the earlier part of the movie, so Oppenheimer just walked around in his neighborhood and suddenly he met Einstein. So basically, like in that neighborhood is called like the complex neighborhood in the Institute for Advanced Study, and also he lived there also. So like a bunch of geniuses of the century, they live together in that area. So like that's how Oppenheimer met Einstein, like randomly in their neighborhood, right? And yeah, so anything, can you kind of guess like who is this guy? Because if we are talking about CPU architecture, we will come for these guys. Um, okay, so I will not let you to guessing more. So this guy's name is von Neumann. So von Neumann is basically a German name. So
Oh,
he's a yeah. So he's a Hungarian, but because you know Austria and Hungarians like both usually before World War I they are one empire, right? Ruled by the Habsburg. So this is von Neumann. So if we are talking about von Neumann, so uh, so we have a CPU and we have a memory. So they are a very integrated part. So if you want to make a CPU functions, you need a memory. There is no such thing as a CPU without a memory, right? So for the next part, we want to try to understand what does this means, because this is like a bunch of like binaries. But now after this presentation, we will understand this, right? So first, every 8 bit has a sequence number. So bit is like one digit here. Bit is binary digit. So bit binary digit. So one bit is every 8 bits or 1 byte have a number. So this is a sequence number 0, 1, 2, 3, 4, 5, 6, 7. Okay, so in binary. So this sequence number is called an address. So every byte has an address. Okay, and so we have address bus here. So like now imagine, so address bus for 3 bits, 3-bit address bus. So it means that in this address bus, we have 3 lanes, right? 3 lanes, 1, 2, 3. So if we only have 3 bits of address bus, so it means like if the CPU wants to access, for example, this particular guy here, 1 byte here, so it will try to put the voltage like 110 in its address bus, and suddenly this byte here, 0110 and stuff, it will be transferred in the data bus. So the data bus is 8-bit in this particular case. So 3-bit of address bus and the data bus is 8 bits or 1 byte. So in this particular case, so it means because we only have 3 bit of address bus, we only have 8 bytes, right? So this is like the memory of 8 bytes. So what does it mean? Okay, so and then we also talk about the CPU bitness. So we know the CPU have 8-bit CPU, 16-bit CPU, right? 32-bit CPU, 64-bit CPU. What does it mean? Is it means that does it relates to the address bus? Does it mean that we are talking about 3-bit CPU now? So we will talk about this later. But now we have different representations. So for example, this is binary, and this is hexadecimal, right? So like computer only knows about binary, but we usually use hexdum. So why is that? Because if you are using binary, it will be too long. So that's why we are using hexdum. And in hexadecimal, one character is 4 bits. So that's why 2 hexadecimal characters is 1 byte. So this is very important. And sometimes also in hexdum, not every bytes we put the address. So usually like we only put the first address, and then we don't put the address here. But now in the fourth address, we will put it, right. So like 0, 1, 2, 3, and then 4, we put the address here and stuff. So this is usually like the format when we are using hexdum. Okay, so now we are talking about instruction set, okay, which telling us a hint that inside a memory there are 2 types. The first type is that might be an instruction. So this is might be an instructions, or maybe something else, somewhere else, it should be a data, right? So what kind of instruction? So let's create our own. So let's create our hypothetical CPU, a very simple hypothetical CPU. So for example, 1001 is a mov, 0011 is add, and sub is 1100 and everything else, right? So what is mov? So mov is basically this one, 1001 AAAA. So AAA is 4 bits, okay? So basically, I want to move 1 byte as specified by this address to register 1. So what is register then? So inside the CPU, there are a bunch of register. So if you want to do an arithmetic, you must put the data from the memory to the register, because in the register, it is connected to the associated with the circuitry, right, for the arithmetic circuits and everything. So if you want to do arithmetic operation, you must put it to the register first. So this is how you do it, 1001, and the address you want to move it to the register. Okay, and then add is basically just putting whatever address as specified by here to our R1. So basically, it is like R1 equal R1 plus the address, the content of this address, and then sub is the other one, and then knob is basically 0000, right? And again, because this is binary, too long, so we can use hexadecimal here, right? So now, what does this mean? So we can just translate it, right? We can just translate it. So basically, what is 1001? Oh, 1001 is mov, okay? So 0011 is add and everything. So this is actually a valid instruction. So this is what CPU does. When you turn on your computer, even without any operating system, the CPU will start working by itself by fetching an instruction from address 0, and then it will try to execute whatever the meaning of the instruction. So this is very important. So my point here is, yes, CPU can work without any operating system by itself. Okay, so now, so what does this mean? So let's disassembly this, right? If we apply this translation, so this is the meaning of our peculiar binary there. So basically, this is mov 5. So remember, AAAA is the address. So mov the address 5. So this is the address 5, which is 200. Okay. So in the raw form, look at this. This is 200. 1100 is actually 200 in binary form, right? So I promise I will not show you that binary again. So this is so much easier, right? The disassembled versions of the binary. So basically, we are just putting 200 to our R1s. Okay. And then we are adding 6, which is 99. This is 99 to our R1. And then we are sub 7 is this 2 to our R1. So this is basically an arithmetic operation. And then after that, no operation is not doing anything, and then not doing anything again. And what happened next then? Okay, our CPU is pretty much dumb. Our CPU doesn't know whether this is a data or an instruction, right? They don't know. So what will happen? So because 200 is 1100, which is a sub, so our CPU will try to do a sub, which is actually not valid. So this is like this is a very simple CPU. It doesn't do its jobs, but yeah, basically this will be an error, right? But this is our first introduction to how CPU works without any operating system. Okay, so other than the R1, which is called the general purpose register, right? The general purpose register is registers that can do arithmetic or like bitwise operation or like shifting operation, right? And then also, I will introduce you with an IP or instruction pointer. So instruction pointer is a register that contains the address of the instruction that that the CPU will fetch. Okay, so for example, if it contains 0 when we are first starting it, so it will fetch the instruction from the 0 address and try to execute it, and then it will increment it to 1, and then it fetch again the instruction and again, right? And SP is stack pointer. Stack pointer, we will talk about this later. Okay, so key takeaways. Okay, memory is data and instructions. Okay, and this one is very important. CPU bitness is derived from general purpose register. So if you see why we are using 64-bit now, except I'm using i9. i9 is 64-bit. Why? Because my general purpose register, which is called RAX. So RAX is 64-bit, right? And for example, Arduino, if you know, yeah, Arduino is using ARM. So ARM architecture is only using 8 bits in its general purpose register. So that's why like Arduino is only 8 bits. So bitness of the CPU is derived from the general purpose register, not from the address bus, because sometimes people use address bus. But why this is also important? So for example, in C, we have pointers, right? Or in Rust, we also have usize. So usize is like 64 bits. If you are targeting 64 bits, so usize is also 64 bits. Does it mean that 64 bits use size of 64 bits, does it mean that we are talking about 64-bit as in the address bus or in the general purpose register? So this is quite confusing. So I will talk about this later. Okay. Oh, and then this is also important. So CPU can run without an operating system. And let's try that also now. Okay. So let's go to there. Okay. So I will open something. Let's open a boot ASM. So this is an x86 assembly, right? So previously we are using assembly, but our own dummy assembly, right? And remember, because like every CPU has its own instruction set. Of course, like ARM instruction set is different than x86 instruction set and different from, for example, PowerPC instruction set. So, and every CPU has its own assembly. So now this is called x86 assembly. And what does it do? So basically, this is we are trying to print this exclamation mark. So I want to run this without any operating system. Okay, so how to do that? Okay, so I will just make it bigger. I will also want to show you the Mac file. So this is a Mac file. So basically, I will run it using KMU. I don't want to use it here. I will use emulator, and then I will try to make it as a bootloader, right? Since let's try it. Make, okay, and okay, and nothing happened. Control AX, Control AX. Why it's not happening? I want to remove. Okay. Maybe I want to clean again. Okay, I know why. I need to change this. Okay, now I will make again. Okay, so now the exclamation mark is printed. So this is basically I boot my computer without an operating system, and basically what our CPU is doing is just taking this instruction one by one, right? Okay. So let's come back again here. Okay. Okay, so now this is yeah, the instruction sets is unique to every CPU. So we have assembly for x86, ARM, Spark, AVR, they are different, they are unique. And then also executable file. So if we are talking about executable files, which is native, for example, we are creating a C executable files like Hello World. So it will be run directly by the CPU. Okay, so usually people will always say that this is run by the OS. No, it is not by the operating system, but by the CPU. So how it is from the file it is being loaded. So the operating system is only loading the content of the file to the memory, and when it is in the memory, the CPU will execute it directly, right? So, but maybe one of the questions that's about like how the CPU can run it directly is because of the security issues, right? If our instruction is executed directly by the CPU, then what if we are doing some kind of malicious instructions? Because CPU, they don't know whether this is malicious or not, right? So that's why in x86, there is something called protected modes. So the protected mode needs to be activated beforehand, and then it will be quite secure. So any kind of malicious codes, it will be rejected by the CPU itself. Okay, so now we are talking about x86, 64, of course. So now before x86, 64, we are talking about this white area, right? This is all of the registers. Okay, so this is called EAX in 32 bits. So this is RAX. RAX means all the whole 64 bits. This is new in 64-bit system. But before, when we are talking about pre 64-bit, so we are only using 32 bits. So this is called EX. This is all the general purpose register: EX, EBX, ECX, right? And we don't have EH, E9. This is new in 64 bits. Okay, and then for floating point, so in our register, we cannot do any integer. So this is only for integer operation, but for floating point, you are using something else like this one. So this is for floating point registers, and this is for the instruction pointer, and we are also using SIMD register, right? So if you are using maybe Python and NumPy, and then they will always ask you if you want to do matrix multiplication, please do not use for, right? Please do not use looping. Just use the function that provided by NumPy. It will be so much faster. Why? Because they are using this a special register called factorization register, SIMD. So usually factorization register is very wide, right? It's very wide. Okay, so when we are talking about 64 bits, so we are talking about RAX, RBX with R in the front. So all of this is 64 bit. Okay. Okay, so now this is one of the example in our Intel operations. So this is 32 bits. So same operation that with our hypothetical CPU, but now this is the real x86, right? So we are putting 200 to EX, okay? We are putting 99 to EBX, and then we are adding EBX to AX, and then the result is also in EX like this, okay? Basically, this is the meaning, and then we are subtracting the EX to 2. So that's and the result will be in the AX itself. So yeah, same code, but in the real x86 instruction. So now what is the main advantage of using 64-bit registers, and why not just using 32-bit? Of course, because now our register is 64-bit wide, okay? So this is in C. We are using long. So in C, long means 64-bit, right? So this is C equal A plus B. So it's pretty simple. So A to RDX, B to racks, and then you just edit, and then you store the result back to the C, right? So this is pretty simple in 64-bit. So if you are targeting your compilation to the 64-bit CPU, this is the result, right? Okay, so maybe why I'm using global variable here, not the local variable. The answer is very simple, because local variable is using stack, right? If we are using stack, then the instructions, the generated instruction will be a little bit complicated, okay? So that's why I am using global variable now, right? Because I'm avoiding using stack operation. So now this is x86, 32 bits. We don't have 64 bits. We can still perform a 64-bit operation, but of course it will be longer. And of course we need like we need to combine like several registers to do that. So I don't want to like explain the details, but basically we can still do that, but with a longer operation. So that's why, like, if you are using if you are doing a 64-bit operation in 64-bit CPU, of course it will be faster. Does it mean we can do 128-bit of operation? Yes, you can, but you need to like combine several register of your 64-bit register, right? So yeah, so set it. And please understand this one, like how fast is our CPU? Because now we know that CPU is just fetching the instruction from the memory, right? Then how fast is this fetching? So the answer is actually very simple. You can try it by yourself. You can just doing the looping for I up until 100 million. So if we are doing several hundred millions, you will feel the delay, because usually the speeds of the instruction of the CPU is like notated as MIPS, million instructions per second. So for example, my i9 is 300, so it means 300 instruction per second. So it's very fast, right? Okay, so now this is a memory address. Okay, so we are talking about x86 64 now. So address bus in x86 64 in my laptop is not 64-bit lane, right? Because 2 to the power of 64 is a very huge number. It's a very huge number, okay? So instead, our bus is only 48 bits, which is only 256 terabytes. So it's not 2 to the power of 64, but 2 to the power of 48, okay? But, so this is important. In C or C++, if you are using address, or if we want to notate any kind of address in x86 64 system, we are still using 64-bit number. So why was it, right? So how to translate it to 64 bits to 48 bits? Okay, so this is something called canonical address. Not really important actually, but basically because we are not using several bytes. So this is a simpler example. So for example, our address, we notate our address with 4 bits, but actual in our system we only have 3 bits, right? So it means we can like make some kind of system. Basically, we are neglecting the first 2 bits, okay, of our address. So basically, it is either 00 or 11, right? So this 2 bit becomes only 1 bit, right? So for example, it is either 00 or 11. So there is no such thing as 01 or 10. So basically, we are like making this 2 bit becomes 1 bit. So the effect is basically this. So this is like a full-blown 4 bits. So you have 0000 up until 11111. You have this. So if we have 4 bits, it means we have like 16 bytes, right? We have 16 bytes. But because we are using this kind of addressing, canonical address, so basically the first 2 bits needs to be duplicated. So this and this part is the only mappable. So this is mappable, and this is also mappable, and this is not mappable, right? So this is how canonical address work. So this is invalid, this is not addressable, but this is addressable. So if we are using our system, this is in x86 64. So of course, like the address is from 0 up until to this, like 1111111, like 64-bit times, right? 64 times. But because as we know, 2 to the power of 64 is too large, okay? So we are not using that. So basically, the first 16 bits, we are not using it. So it's either all 0 or all 1, right? Which means we can only map this, the higher one. So if we can come back here again, so we have the higher part. Sorry, this is the higher part. This is 0, right? So this is the higher part, and we have the lower part, and we have a hole in the middle. So in our system, it's only also like that. We have the lower part, which is 128 terabytes. We have the higher part, which is the last 128 terabytes, and we have a very massive hole in the middle, right? So this is why it's called canonical address, and this is how our address is still notated as a 64 bits, but there are several non-addressable address like this in the middle. So it's very easy. If you see, it is either FFFF or 000, right? If you see variety of that, for example, like 00RC something, other than FFFF or 000, it is not valid address. Okay, so now we will talk again about the CPU bitness. So why x86 64 is a 64-bit? Because our GPR is 64 bits, okay? Even though the address bus is only 48 bits, okay? And then if you still remember the console war back then, so we have PlayStation 2, we have Dreamcast. They claim that PlayStation 2 uses 128-bit, okay? Dreamcast, they claim they are using 128-bit also. So it's actually not true, because Sega Dreamcast, they are using Hitachi SH4, okay? So Hitachi SH4, they are only using 32 bits. So no, it's only a marketing jargon. As well as PlayStation 2, they are also using only 64 bits, actually, the general purpose register. So this is also only a marketing jargon. So why they can claim that? Because it is not the general purpose register, but the SIMD register. If you still remember SIMD register, they are usually Y, okay? So also, in our case, using the same logic, our i9, we can also say Intel i9 is 512 bit, okay, with the same logic, because if we can use our SIMD register with 512 bit wide in i9. Okay, so let's see, like what time is it now? This is 11. Okay, so we have 30 minutes left. Okay, so now before we talk about Linux process, so we need to understand something called protected modes, because this is what makes our operating system secure. So we will talk about ring levels, okay, interrupt space tables, and then we should understand that user space and kernel space is different, okay? And then ring levels is associated with privileged codes and non-privileged codes. So that's why, like, for example, your driver is run on kernel mode. So in kernel mode, you can do anything because you are God in kernel mode, right? So we will talk about that. And if you really want to know about that, so there is a YouTube videos here. So when I first know about this, I read the Intel manual. So actually, from the manual is very complete. But now I think like these videos is very good and simpler. So I think if you really want to know like how to create your own operating system, you can just as a prerequisite, you can just open that for x86, right? For 64 bits application. So I just want to say something a little bit here. We won't deep dive on this, right? Of course, like this is like a bunch of registers you need to understand if you want to enable the protected mode. So for example, how to enable the interrupt table. Okay, and then we have also called the global descriptor table, okay, and all of this stuff. And then if you want to enable the virtual address, you need to understand also about the page table here. So you need to set up here these registers before your operating system is started. Okay, so now I'm talking about the kernel mode and the user mode, right? So in x86, there is something called ring levels. We are talking about hardware, right? So in ring levels, we have 4 ring level: 0, 1, 2, 3. Okay, so 3 is the least privileged, and then 0 is the most privileged. Okay, so our user applications, every application, our Hello World application, even our GVM, okay, even my Windows Manager, if you know Xorg, for example, or Wayland, this is a window manager. We think that this is kind of like a kernel stuff. It is not. It is a user space application. So it runs on ring level 3, okay, less privilege. When they want to do something, they will invoke something called a syscall. It will call a syscall. It will be handled by the kernel, and the kernel will run on ring level 0. So in Linux, we have 0 and 3, okay, and 1 and 2, we don't use it. I don't know any other operating system that use 1 and 2. Even in Windows, also 1 and 2 is not used at all, right? Okay, so that's it. And then like, where does the ring level, the current privilege level is stored in our system? Okay, so I just want to tell you about that. So we have these segment registers. Okay, we have CS is code segments, DS is data segments. So CS, inside the CS, these ones, okay? So inside the CS registers, okay? So we have this RPL, requested privilege level. In CS, this is not CS, but in CS, this is called CPL, current privilege level. Okay, so in CS, if we somehow can manage to change it, for example, from 3 to 0, so now we will run to kernel modes, but we cannot do that. We cannot just use mov, right? We cannot just use mov like 0 to FS. No, we cannot do that, because if you want to change CS, you can use it by, for example, doing a syscall, doing a long jump, etc. So that's it. So of course, I will not deep dive on this. And this YouTube is very good, so by the way. Okay, so now Linux process. Now that's the real deal now. Okay, so because we are talking about the process, we are talking about two sides of the process. Sometime when we are compile, for example, from the Rust code or from the C code, the compilation's output is a native binaries, right? The file. We are talking the binary as in the file, and we also talk about the binary when it's actually loaded to the memory. So these two are separated. So there is an application called Radar. So this is Radar. And then, for example, the main here is the binary file that we want to disassemble. So when we are using Radar main, and this is the output of the program, right? Radar is basically a quite fascinating application, by the way. So it is not only for disassembling, but you can do much of everything. So now I have a question here. We already know from before, right? That this must be an instruction. Must be an x86 instruction. So what about this? Okay, maybe this is a memory address, or is it? Because we are talking about file now. Okay, so we are talking about file. Maybe this is a file offset. Okay, maybe this is like a 0 bytes from the beginning of the file. Maybe this is a 1,000 bytes from the beginning of file. Maybe this is not a memory address. Maybe. Okay, so I will answer this question later. Okay, and 55 here. If you still remember, this is the binary representation of the content of the file, right? So what is 55? So if you still remember, this is the hexadecimal. So 2 hexadecimal characters is 1 byte. Okay, so that's why like push RBP is basically 1 bytes of the memory. If the instruction is only 1 byte for push RBP. Okay, so whatever it is, maybe whether this is an offset or this is an address. So we can see whether this is 39. Okay, so because this is only 1 byte, so the next will be 30A. Okay, so this is 30A, 30B, and then 30C, and 30D here. So yes, so this is basically like each 2 characters of hexadecimal is 1 byte. So that's it. Okay, so now before we are talking about whether this is a file offset or a memory offset or a memory address, let's talk about ELF file. It's a binary file used in Linux, in Unix, and pretty much like many other operating system. So this is called ELF, okay, executable and linkable file. Okay, so of course, like before we are talking about this, what is inside the binary file? As we already know, of course, the content of the executable file is the instruction itself. Maybe it's a data, and then it will be loaded by the operating system to the memory, and it will be executed directly by the CPU. So now, how the operating system, or maybe how the program to load this file? Like, what is the mechanism? So first we have the header, okay, and then we have the program header table, aka segment, okay, and we also have sections here, okay. So sections is important if we are writing in assembly. So section is important if we are writing in assembly, or if we are a linker. Okay, so the linker will use every section to combine them together. For example, what I mean about linker is because when we are compiling stuff, usually the output is multiple files, right? And these multiple files need to be combined to become one binary. So that's why it's called linker. So they link together. They combine all of the text in each of the separate compilation outputs to become one. They combine all of them to become one super section here, like .text in the output executable. So yeah, so that's like how the linker works. But we are not talking about linker now. We are talking about the loader. Okay. So for the loader perspective, we don't need a section. We only need a segment or a program header table here. This is a program header table. So look at this. This like 2 sections, 1 segment, right? So 1 segment is consists of several sections. So that's very important. So I will also tell you what is this .text.ro data. So .text means instruction. Okay, so it contains an instruction. .ro data means it's a read-only data. Okay, .data means it's a global variable basically. Okay, so that's what it means. But again, in segment, we don't have a name. We only have like where it's where the segment is start, when it's end. And let's deep dive on it here in this diagram. I love this diagram. This is only one diagram. It's very concise. Okay, and I will show you how this program is loaded to the memory. Okay, so let's try this. I will open that to make it bigger. Okay, so now look at this. So basically, before we start everything, what we are trying to do is this. We have a file called simple.arm. Okay, so when we are executing this uname -m, so uname is basically we are showing our current system, which is now ARM version 7, which is like Raspberry Pi is usually ARM version 7, right? But not your mobile phone. Your mobile phone is much more complicated than just ARM 7. So basically, this is an ARM binaries. Okay. So again, so how does it? How this application is loaded to the memory? Okay. So let's see. The loading process. We have 1, 2, 3. As simple as 1, 2, 3. So first is the header. You locate the header and try to understand. Okay. And then the header consists of two: the ELF header and the program header. Okay. And then from the program header, you try to map the memory. You try to allocate the memory. So the content from the file, you copy that to the memory. Okay. And then after that, you execute it. Okay. So let's make it more elaborate. So this is the content, our content of simple ARM, which is very simple. Look at this. This is maybe only several hundred bytes, right? Remember, 2 hexadecimal characters is 1 byte. So maybe it's less than 100. Maybe I don't know. Maybe it's less, right? So again, so we have header, we have sections, we have also like header in the bottom, right? So this is called section header. If you still remember the previous diagram. But again, we try to load this file to the memory, so we don't care about section header. Okay, so let's look at the header. So this is the header. Okay, so this is the DOM. So this is the header. Okay, so look at this. This blue area here corresponds to this. So this is like the signature of our ELF, the signature of ELF. So this is like a valid ELF because it contains a signature. And then also among several other, which is quite important, is for example, this is ARM, right? This is ARM processor. So this blue, right? This blue 28 means ARM processor. So even though in my laptop, I'm using Linux, okay? Maybe I can just copy this file in my laptop. But if I try to run this file, of course, it won't be run because my laptop is x86, while the content of this binary file is an ARM instruction. So of course, like my laptop will not be able to run this binary, right? So that's why it's very important that we match our uname, which is ARM, and with the contents of the file. Okay. So what is the most important part is this: where is the program header is located, right? So where is it? Program headers offset. So this is it, like 40. So we can locate the program headers offset, and then like how many contents of our program header. Okay. Okay. So let's come back again here.